Okay, so today we're gonna start a new section, namely section 7 in our lecture notes, ordinal numbers, which is, at least for me, the most important part of the course. When I asked the people who designed this course why the catalog was the way it was, they told me like the main point was basically to teach you the cardinal numbers. Like you should be able to count how many elements are there in a set, and you should be able to make comparisons between sizes of sets. And in order to learn cardinal numbers, you need to learn about ordinal numbers. In order to learn about ordinal numbers, you need to learn not all the stuff we have done so far, but maybe most of it, okay? So this is why if you are not feeling comfortable with all the topics that we have covered up to now, you should study before it's too late, okay? So let's start ordinal numbers. Now, historically speaking, the point of ordinal numbers was to understand well-ordered sets, okay? So we want to understand the structure of well-ordered sets. Ordinal numbers are, whatever they're going to be, they're supposed to represent well-ordered sets, okay? And what people did back in early 1900s was that because you want these guys to represent well-ordered sets, what they did was they took all the well-ordered sets together, which are isomorphic, and they put it in a single set. But there was a problem. That collection was not really a set. When you collect, let's say, all well-ordered sets which are isomorphic to natural numbers, then that collection is not going to be a set. It's going to be a proper class. So the early ideas was to use to think of ordinal numbers as equivalence classes of well-ordered sets, where every equivalence class consists of isomorphic well-ordered sets. The problem was that such equivalence classes, it turns out that they cannot be sets. They become proper classes. And that brings technical difficulties. I mean, we can use that definition, but then we may have to deal with minor issues because the collections we're going to be dealing with are not going to be sets. Instead, John von Neumann, one of the greatest mathematicians of 20th century, came up with a very simple definition which actually captures the essence of what we want to do. He realized that we don't really need to consider the whole equivalence class consisting of all these isomorphic well-ordered sets. There is a natural way to pick a representative for each such equivalence class. So there is a canonical set that I can choose from such equivalence classes which represent all the well-ordered sets in such equivalence classes. And in order to understand that definition, we have to first learn about the definition of a transitive set. Now, a set X is called transitive if every element of X is a subset of X. In other words, if you have a set which is a member of X, then it's actually a subset of X. Now you can easily check that this is the same as saying that the union of X is a subset of X, because pick an element in the union. An element in the union is a member of X, right? Well, according to this, a member of X is inside X. So this easily implies this. Now go in the other direction. Pretend that this is true, your set is transitive. Then if you pick a member of X, well, if you have a member of X, then that set is a member of some Y, but then every element of X is a subset of X, so that set you picked in the first place, it's an element of X, okay? So it's the same thing. So these are the same thing. Transitive set simply means that every element is a subset, okay? Now what are examples? The empty set is transitive for trivial reasons because empty set has no elements, which means that if you put empty set for X in here, this part is automatically false, therefore this implication is automatically true. We have a vacuous truth. In general, okay, what is empty set? It's the set 0. It's a natural number. It turns out that all natural numbers are transitive, okay? And I'm going to assign this as an exercise. Show that n is transitive for all n. Show that every natural number is transitive. Okay, this is an exercise, but pictorially this should be clear. Why? Let's pick some natural number, successor of some n, okay? If you pick an element, let's say you picked 3, you know that what is 3? 3 is the set of 0, 1, 2. So 3 is not only a member of this guy, it's also a subset of this guy. Because every natural number consists of all the previous natural numbers, this is going to be true. Every natural number is transitive. What other transitive sets do we have? Well, we're going to learn about a huge class of transitive sets, so I'm not going to give more examples, okay? I mean, I can construct artificial examples if you want, which satisfy this, but I don't want to because what we're going to call ordinal number is automatically going to satisfy this. This will be a part of the definition, okay? So that's that. Any questions about the notion of transitivity? Yes?
Rational numbers and real numbers are also transitive.
No.
No?
No.
Don't they contain previous numbers?
Well, containing previous numbers it's not the point. Containing all the elements of themselves is the point. If you pick a real number, it's a dedekind cut. Okay? So its elements are rational numbers. If you pick an element of that rational number, then that's an equivalence class. Is that equivalence class in the whole thing? No. So the definition of being transitive is not that you contain all the previous numbers, because you don't have to deal with numbers. You're dealing with arbitrary sets. This is the definition. Every element should be also a subset. Okay? So real numbers, rational numbers, they don't satisfy this. At least not the way we constructed them. Other questions? This is a prototypical example of a transitive set. And we're going to see more examples, as I said. Okay, now, here comes the main definition, which you should not forget. A set alpha is called an ordinal. Now, there's this tendency among set theorists to use Greek letters alpha, beta, gamma to denote ordinal numbers, okay? And when I use kappa, lambda, and so on, those are going to denote cardinal numbers, okay? So in future, it is possible that I may forget to write that blah blah is an ordinal number and simply use the letter alpha. From now on, if you see an alpha, you should assume that that's an ordinal number, unless I say otherwise. Anyway, a set alpha is called an ordinal if an ordinal number if an ordinal number is simply a transitive set which is well ordered by its membership relation. And when I say well ordered, I mean strictly well ordered. this is a strictly well-ordered set, okay? So von Neumann's realization was that within all those equivalence classes which contain isomorphic well-ordered sets, I can actually find one which is transitive and which is well-ordered by the usual membership relation. Now, there was an exercise which I assigned a long time ago, but I remember that exercise being on this board probably like 3-4 weeks ago, I don't remember. It was that every natural number with the membership relation is well-ordered. Now, this exercise shows that every natural number is transitive. So if you combine those two exercises, you will realize that the natural numbers are ordinals. So these are some ordinals. Every natural number is an ordinal, okay? Now, what other examples do we have? We're going to prove that the class of ordinal numbers, it's a proper class, it's not a set. So there are actually too many ordinals. But before I do that, I need to prove some abstract lemmas. At this point, the picture of ordinals, whatever that is, it should not be clear to you. And it's going to stay that way for some time. For now, the only examples of ordinals you know are these guys, okay, natural numbers. I'm going to construct more, but before that, I want to prove various basic facts about ordinal numbers. Oh, maybe one more example. The set of natural numbers itself, it's an ordinal, because we already know that this is well-ordered by the membership relation, because we defined the strict linear ordering on this to be the membership relation. So this, we know that the second condition is already satisfied. That was a theorem which we proved by induction. And that this is transitive is easy because I'll pick an element of this. It's a natural number, but the elements of that natural number are natural numbers themselves. So this is easily seen to be transitive. So this is itself an ordinal number. Okay. Now, let's leave the examples for now. So these are the only ordinal numbers you know at this point. Let me prove some basic lemmas which directly follow from the definition of an ordinal number.
So, every ordinal number is like a set, right?
Yes. Well, everything we deal with is a set. So now let's start with this lemma. If alpha is an ordinal, then so is successor of alpha. Okay, so what do I need to show to say that something is an ordinal? I need to show two things, that is transitive and is strictly well-ordered by the membership relation. Okay, just because saying strictly well-ordered involves 3 words, whereas saying well-ordered involves 2 words, I might in future like unconsciously say well-ordered where I mean strictly well-ordered. At this point, you should be aware of the difference, okay? So when I say an ordinal is well-ordered by the membership relation, you understand that it's strictly well-ordered, not really well-ordered, because we made a distinction between them. Okay? So while talking fast, I might just ignore that word unconsciously. Anyway, so let's start with an ordinal number. Now, we wish to show that this is an ordinal. How do you show that something is an ordinal? You show that it's transitive and strictly well-ordered. Let's pick, what does it mean for a set to be transitive? The elements of that set should be inside that set. So let's pick an element of this guy, and let's pick an element of that. Let's pick a gamma inside this, and let's pick a delta in that gamma. Now, gamma is a member of successor of alpha, which means that it is either an element of alpha or it is alpha. Okay? In the first case, we have gamma in alpha and delta in gamma, but alpha is an ordinal number, so it is transitive, which means that this guy is an alpha. Delta is an alpha, as alpha is transitive, okay? So in this first case, because alpha is transitive, an element of its element is a member of alpha, but then, well, alpha is also a subset of S alpha, which means that delta being an alpha implies that delta is in S of alpha. Okay? Now in the second case, if gamma is alpha, then gamma is already inside S of alpha by definition. Now in both cases, I got that this delta is in S of alpha. Thus, S of alpha is transitive, okay? We now need to show that S of alpha is strictly well-ordered by the membership relation. Now, writing that part in a precise manner, formally, it's tedious, it's boring. So I'm going to assign that as an exercise, but show you why this is the case. Exercise. Show that this guy is strictly well-ordered by the membership relation. Hint, let me tell you the reason. This well-ordered set is obtained by adding one more element, namely the element alpha, to the strictly well-ordered set, alpha as the greatest element, okay? Now, look at this well-ordered set and look at this well-ordered set. Look at S alpha with the membership relation and look at alpha with the membership relation. This guy only has one more element. And that element is greater than all the previous elements. So what you do is, in order to obtain this guy, you simply add one element to this strictly well-ordered set. You add it to the very end, okay? You basically add a greatest element. Now here's the question. If you have a well-ordered set, and if you add one more element to the end, meaning that you add a greatest element, okay? You simply say that I'm going to enlarge my set and I'm going to change my relation, the well-ordered relation. I'm going to define this added element, I'm going to make this added element strictly bigger than all the other guys. Can this new partially ordered set be not well ordered? No, because what does it mean for a set to be well ordered or strictly well ordered? It's supposed to be a strictly linear order relation where there is no infinite descending chain, right? There are no elements of the form alpha 1 greater than alpha 2 greater than alpha 3 and so on. We prove that equivalence. Now, if you're the greatest element, you can't create an infinite descending sequence which didn't exist. Because, let's say that in this bigger guy, there exists an infinite descending sequence. Like, if you see the greatest element you added, alpha, at some point in that sequence, then that's fine. Cut the sequence at that point. Look at the rest. The rest will have to contain the old elements, which were already there. But if you restrict your attention to that part of this infinite descending sequence, then that's an infinite descending sequence in this set. So this can't be well ordered if this is not. So work on this. It should be clear why this is well ordered when this is well ordered. So work on that at home. This is an exercise. Now this is an easy lemma, but it is actually powerful because it helps us construct more ordinals. Let's add examples. Okay. For reasons that I'm not going to explain, because I don't know the actual reasons, I am going to show this set natural numbers from now on with the Greek letter omega, okay? From now on, when I use omega, you're supposed to understand the set of natural numbers. Now, these were the ordinals I knew so far, and by this lemma, okay, this is an ordinal. I can take its successor, and this is an ordinal as well, okay? What is this? This is the set of all natural numbers together with the set of natural numbers itself, okay? And the successor of omega, this is an ordinal as well, okay? Because that lemma tells me that. And because this is an ordinal, I can take the successor of this guy, and this is an ordinal, and I can keep doing this. Now, I want to put something over here, but at this point, I don't know I can do that. Indeed, with our current machinery, you can't create the next ordinal. We will need another axiom called the axiom of replacement, which will be the last of the ZFC axioms that we're going to learn. But we're going to talk about that later. Let's now prove more abstract theorems about ordinals. Okay, is this clear? When you have an ordinal, when you take the successor, it is still an ordinal, okay? Good. So, what do I want to do? I'm going to erase this board. I think okay. Oh, one more exercise. Okay, I'm going to write it over here together with a theorem. This is the main theorem we want to prove today. Let me assign the exercise. If you Google term ordinal number, you will realize that some sources define ordinal numbers in some other way, okay? Ordinal numbers have many equivalent characterizations. They're all equivalent if you assume all the axioms we've introduced so far. If you drop the axiom of foundation, sometimes they are not equivalent, but because we're going to assume axiom of foundation, we're assuming axiom of foundation, all the characterizations that you can find online, they're the same. I don't want to introduce all of them. I'm just going to introduce one, namely the following. Prove that a set is an ordinal if and only if alpha is transitive and for all gamma, delta, and alpha, we have that gamma is inside delta, or gamma equals delta, or delta is inside gamma. So an ordinal number is simply a transitive set whose elements are comparable with respect to the membership relation, meaning that either one of them is a member of the other or they're the same. Okay? So we actually didn't have to refer to strictly well-ordered sets at all. Now, prove that this is the case. Here is the main theorem I want to prove. Given ordinal numbers alpha, beta, and gamma, we have, let's see, if alpha is a member of beta and beta is a member of gamma, then alpha is a member of gamma. If alpha is a member of beta, then beta is not a member of alpha. And we have that either alpha is a member of beta, alpha is beta, or beta is a member of alpha. And the fourth bullet point, the last bullet point, is this. Every non-empty set of ordinals has a least element with respect to the membership relation. Now, we're going to prove this, but before that we need to prove several lemmas. But let's first understand what this says. Well, it says what it says, but let me tell you what it really says. It says that the class of ordinal numbers is strictly well-ordered by the membership relation. Now, I'm going to put this in quotation marks. Here's the reason. What's a strictly well-ordered set? It's a set together with a relation satisfying blah blah properties. Because the class of ordinal numbers is not going to be a set, as we shall see, I can't really say that the class of ordinal numbers it's a strictly well-ordered set, because it's not a set at all. However, it behaves exactly like a strictly well-ordered set with the membership relation. What do I mean by that? If alpha is, think of this as your less than relation. If alpha is less than beta, then beta is not less than alpha. If alpha is less than beta and beta is less than gamma, then alpha is less than gamma. So these two properties simply say that the class of ordinal numbers together with the membership relation, it's a strictly partially ordered set. Now, when you add this property, given two ordinal numbers, they're comparable with respect to this relation. These three bullet points simply say that the class of ordinal numbers, it's a strictly linearly ordered set. When you add the third property, every non-empty set of ordinals has a least element with respect to relation. You're simply saying that the class of ordinal numbers, it's like a strictly well-ordered class, okay? It behaves exactly like a strictly well-ordered set. The only difference is that it's not a set, okay? So the class of ordinal numbers, together with the membership relation, it is a strictly well-ordered class, meaning that it behaves like a strictly well-ordered set. Is this understood? Now this is important because we're going to use this a lot, okay? For example, in future, we shall say things like, there exists an ordinal satisfying blah blah property. Therefore, there exists a least ordinal satisfying that property by this fourth bullet point, okay? Which used to happen in strictly well-ordered sets because every non-empty set had a minimal elements and so on. Now we want to prove this, but well, we're going to prove this, but we need some lemmas. Any questions about this? Are you sure? Okay. Now, you will probably object. You might want to object at this point that some of these bullet points are trivial, as in, if alpha, let's assume that alpha is a member of beta and beta is a member of alpha, then this can't happen by axiom of foundation, right? We proved that we can't have two sets which are members of each other. However, the point is that all the proofs I'm going to do, they are not going to use axiom of foundation, okay? So this theorem holds even without the axiom of foundation. With axiom of foundation, this is easily proved, okay? Because you can get rid of this bullet point easily and this bullet point easily. It makes some part of this theorem trivial, but this is actually true even without the axiom of foundation. That's the point of me proving all these lemmas that I'm about to prove. For example, we know that there is no set which is a member of itself, right? That by axiom of foundation. In particular, it is true for ordinals. However, this statement for ordinals is true even without axiom of foundation. It simply follows from the definition of being an ordinal. Assume not. Let alpha be an ordinal such that alpha is a member of alpha. Then well, alpha is a member of alpha, which means that alpha is related to itself. Well, alpha is an element of itself and it's related to itself, so it is, well, alpha is related to itself with respect to the membership relation on alpha, which means that this relation cannot be asymmetric. Why? What does asymmetric mean? If A is related to B, then B is not related to A. Can this relation be asymmetric? If A is related to B, then, well, B is related to A somehow. So this cannot be asymmetric. So just by the fact that an ordinal is well ordered with respect to this relation, we get that an ordinal cannot be an element of itself. Okay? So that's that. Let's prove the next lemma. So no ordinal is an element of itself. Well, no set is an element of itself, but for ordinals, this is true, as I said, without axiom of foundation. This simply follows from the definition of being an ordinal. Let's prove the following. If alpha is an ordinal and gamma is an alpha, then gamma is an ordinal. Now, these lemmas might seem abstract at the moment. You might not understand what they mean, but when I draw the picture of ordinals using these lemmas, these will get clearer, okay? So for now, just bear with me and let's prove all these lemmas. Then I'm gonna draw a picture of ordinals, and you're gonna understand. Oh, this is why we proved this lemma. For example, this lemma says what? If any element of an ordinal is an ordinal itself. Just think of natural numbers. What's a natural number? It's the set of all previous natural numbers, right? Ordinals are going to behave exactly like that. And an ordinal will consist of all the previous ordinals, okay? An element of an ordinal will be an ordinal. So let's prove this. Let alpha be an ordinal and gamma be an alpha. Now, we wish to show that what? Gamma is an ordinal. What does an ordinal mean? An ordinal is a transitive set which is strictly ordered by the membership relation. So we wish to show that this guy is transitive and this set is strictly well ordered. Let's start with the first one. Let's try to prove that this gamma is transitive. How do you show that something is transitive? You pick an element of that set and you try to show that that element is actually inside. So let delta I'm just going to pick y. I want to be consistent with my notes. Let y be an element of this, and x be an element of y. So let's pick an element of gamma. Okay. Now, since alpha is transitive, we started with an ordinal, so that ordinal is transitive. Which means what? Any member of that set is actually a subset of it. So this gamma is not only a member of this, but it's also a subset. Which means that, well, if gamma is a subset of alpha, then any element of gamma is an element of alpha. So I'm using the fact that alpha is transitive. Yeah, I already used the fact that alpha is transitive. I'm simply using this. Now I have an element of alpha. But alpha is transitive, which means that any member of alpha is a subset of alpha. And so, well, y is a subset of alpha, x comes from y, which means that x is actually inside this. Okay? Up to this point, I only used the fact that alpha is a transitive set. I didn't use the fact that it's an ordinal. I didn't use the fact that it's strictly well ordered by the membership relation. Now I'm going to use that. Let's look at this. X is in alpha. Y is in alpha. Gamma is in alpha. And X is in Y and Y is in gamma. What can you tell me about this relation, this membership relation on the set alpha? It is a transitive relation. Now, you should not confuse it being a transitive set with being a transitive relation. Those are two different things, okay? What did transitive relation mean? If A is related to B, B is related to C, then A is related to C, right? Relation is transitive. Now, alpha is well-ordered, strictly well-ordered by the membership relation. as a part of the definition, the membership relation is a transitive relation on alpha, meaning that if you pick 3 elements of alpha such that one of them is related to the other and that one is related to some third one, then the first one and third one are related, okay? So this simply follows from the fact that alpha is strictly well ordered by membership relation. And now we're done proving that alpha is transitive. We have X and gamma. We picked an element of gamma and showed that that guy is inside. Thus, gamma is transitive. Questions about this part of the proof? Now, I like these proofs because not only they are not difficult, but like you can see how we use each part of this definition of being an ordinal. Okay? Up to this point, we simply use the fact that my set is transitive. Now, then I use the fact that the membership relation is transitive on this set. Okay? Well, I haven't used the other two properties yet. But I will in a second. Okay. Now, I'm going to write some stuff over there in a second. Is strictly well ordered. If you have a strictly well ordered set, and if you pick a subset of this set, then that subset together with the restriction of your relation to that set is still a well-ordered set. It's a strictly well-ordered set. Is strictly well-ordered. This was, I guess, an exercise that I assigned a long time ago, right? When you have a linearly ordered set and you look at the restriction to a subset, it's still linearly ordered. If you have a well-ordered set, if you look at the restriction, it's well-ordered and so on. I think it was on that board. For some reason, I tend to remember where my exercises was on the board. Where my exercises were on the board. Okay, so we have this. However, since, well, the transitivity of alpha implies, you see, this relation, the restriction of the membership relation on alpha to gamma is the same as the membership relation on gamma itself. This should follow from transitivity. And so, what have we obtained? We obtained that gamma together with its membership relation is strictly well ordered. We proved that gamma is a transitive set such that together with its membership relation it's strictly well ordered. That by definition means that gamma is an ordinal number, okay? Now, questions about this? I'm going to prove, let's look, one more lemma, not today, and then we're going to prove this theorem. As I said, this theorem is really important because it tells you something about the global structure of the class of ordinal numbers. Namely, it says that ordinal numbers simply behave like a well-ordered set. I can't call it a well-ordered set because it's not going to be a set, it's a class. But if we define what it means for a class to be well-ordered, then we could really claim that the class of ordinal numbers is well-ordered with respect to the membership relation, okay? And let's see. I need 3 lemmas to prove that theorem, 2 of which I have already proven. The third one I'm going to prove next lecture, but let's understand these 2. The first one says no ordinal is a member of itself, which is true even without the axiom of foundation, because as you can see, the only fact I used here is that this relation is asymmetric. And we then proved that an element of an ordinal is itself an ordinal, okay? In order to show that this guy is transitive, we simply use the fact that alpha is transitive. And in order to show that gamma together with its membership relation is strictly well-ordered, we use the fact that alpha together with its membership relation is well-ordered. Now, I haven't defined the ordering on ordinal numbers, but as you can guess, in future I'm going to define an ordinal alpha being less than an ordinal beta as alpha being a member of beta. Just like we defined the strictly linear order relation on natural numbers, I'm going to say that alpha is less than beta if alpha is a member of beta. And then when I prove the third bullet point in here, which says that any 2 ordinals are comparable with respect to the membership relation, this would simply mean that an ordinal is simply the set of all previous ordinals, okay? Any element of an ordinal is an ordinal itself, and this guy is less than this, which is with respect to the relation that I haven't defined yet. And because I know that any 2 elements are, any 2 ordinals are comparable with respect to this membership relation, the ones that are not in alpha are going to be bigger than alpha. So alpha is going to, this would simply mean that alpha is the set of all previous ordinals. But at this point, I don't know what the word previous means, okay? Now, let's see, make sure that you study all these lemmas and definitions because, as I said, this is like the main core of the course. The topics after this point, including this lecture, ordinals and cardinals. So if you feel that you're not comfortable with these notions, strictly well-ordered sets, or restrictions of order relations which is, to the substance and so on, make sure that you review all the previous stuff, okay? If not all of it, just review the relevant material. There is a reason that we did all that stuff, like the order relation, strictly well-ordered sets, and so on, okay? So I will see you on Thursday.